Hello everyone and welcome back for another Intro to Signal Analysis video. The topic of today's video is how to compute the output of a discrete time LTI system for a couple different types of inputs. So let's get going. Alright, so in this problem we're given a discrete time LTI system and we're given its frequency response. So the frequency response obeys that expression right here. And our goal is to find the output for two separate inputs. The first input consists of a constant plus a cosine plus a scaled and shifted delta function. And the second input consists of just the sum of four scaled and shifted delta functions. All right, so before we get started solving this problem, we want to first observe that the frequency response completely specifies the system. So to see what we mean by this, we're given this frequency response. For an FIR system, we can immediately obtain the impulse response for that frequency response. And I actually have an associated video that does that. So if you don't know how to do that, take a look at that other video. But we can just write down an expression for h of n given this h of omega. So what we do, we know that this 1 here is the coefficient of the component at time 0, which that's just delta of n. And then there's a 1, this is effectively 1 there, and that's 1 there, and that's 1 there. Those are all 1s. Those are the coefficients for the signal at time 1, at time 2, and at time 3. So we just read off here, so that would be plus delta of n minus 1, plus delta of n minus 2, plus delta of n minus 3. So let me make sure that that actually looks like a plus. So plus. Okay, so that's what h of n is, and we could actually do a little sketch of h of n down here. So it's just equal to 1 at these 4 different points, 0, 1, 2, and 3, and it's equal to 0 everywhere else. So given the frequency response, we can immediately find the impulse response. Either the impulse response or the frequency response tells us everything we need to know about the system. Now just remember the definition of the impulse response. The impulse response is what comes out of the system when we put a single impulse at 0 in. So we put delta of n in, we get h of n out. All right, let's see how we can use this information to solve these two problems. Okay, so we know this system is LTI. The input is this x1 of n, and the output is y1 of n. So because it's LTI, we can find the output for each of these three inputs, and then add together, right? That's because it's a linear system. We can always split up the input into a bunch of pieces and solve the problem for each piece, and then just add them back together to get the overall result. So there's a particularly easy piece in this equation, because we just said the definition of the impulse response is the output when the input is an impulse. Well, the input for this piece is an impulse, right? It's a scaled and time-shifted impulse. But again, because the system is LTI, that makes it easy. So we know if we put in delta of n, we would get out h of n. We have h of n, right? We have that from what we did on the previous slide. So if we put in a scaled and time-shifted delta, because the system is both linear and time invariant, that will just scale the impulse response and shift it in time. So it scales it in amplitude by a 10, and it shifts it in time by 3, because the impulse is scaled by 10 and shifted by 3. So we know the output to this term is just 10 h of n minus 3, and we know exactly what that is, right? We know what h of n is. So 10 h of n minus 3 is just going to be, we're going to take the impulse response we had from before, scale it by 10, so now all of these impulses are 10, and now they're going to start 3 points later, so 3, 4, 5, 6. So that's the output just due to this term here. Okay, that's pretty easy to do. So now we have to solve for the outputs for these other two terms, the 5 and the cosine pi over 2 plus pi over 4. And so let's actually move over to the next slide and we'll solve the rest of it. So 5, we can think of 5 is just a constant, so 5 is also equal to 5e to the j 0n, right? It's a zero frequency signal, so it's DC signal. Okay, we know that for inputs that look like e to the j omega naught n, the output is just the value of the frequency response at that frequency times whatever the input is. So we know that the output over here should be h of 0, because that's the frequency, times e to the j 0n. Okay, well that's all fine and good. Well, what is h of 0? H of 0 is equal to, I'm just going to plug in for 0 everywhere I see omega in the frequency response equation. So let's just quick look back. So the frequency response, got to go one more page. The frequency response is this expression, so I'm just plugging in 0 for each of these terms. So h of 0 is going to be 1 plus 1 e to the j 0 minus j0 plus 1 e to the minus j20 plus 1 e to the minus j30. Well, the e to the j0 terms don't do anything, so we sum all these together and we just get 4, because e to the j0 is 1. Alright, so we get 4. So the output here is 5 times 4, which is 20, times e to the j0n, which is just 20. So the output for this constant input is equal to 20. Okay, pretty easy to do. Now we're going to use the same property, the same eigenfunction property basically, or the same definition of the frequency response to solve for the next term, which is the input is cosine pi over 2 n plus pi over 4. We can take advantage of the fact that we know this is a real system. It has a real impulse response, which means that we can write the output here as h, the magnitude h of pi over 2, times cosine pi over 2 n plus pi over 4 plus whatever the phase of the frequency response is at pi over 2. Okay, so let's first find h of pi over 2. H of pi over 2, just plugging into our equation that's well known for h, 1 plus e to the minus j pi over 2 plus e to the minus j pi over 2 times 2 plus e to the minus j pi over 2 times 3. That's just plugging in with pi over 2, okay, to our formula for the frequency response. We're experts at complex numbers now, so we can reduce this. This is 1 plus e to the minus j pi over 2 is actually minus j. This is e to the minus j pi, which is minus 1. This is e to the minus j 3 pi over 2, which is plus j. So this whole thing is 0. So the output for this term is just going to go to 0. Okay? And that's because the frequency response is equal to 0 at pi over 2, and that's the frequency of the input. So we can write our total answer now. Y1 of n is going to be equal to, let's just on the previous page, it's going to be equal to 10 h of n minus 3. It will be 10 h of n minus 3 plus the 20, and then plus the 0. Okay, so that's really 20 plus h of n minus 3, which we could easily do a sketch of if we wanted to. Okay, so this was a pretty straightforward question to solve. We were solving for the output when the input is equal to this, and we took advantage of the definition of the impulse response to solve for this piece, and we used the definition of the frequency response and what we know about that to solve for the output for each of these two pieces. Okay? So this is the answer to the first example. All right. So we have one more problem to solve regarding this particular system, and now we want to look at finding the output when we have a different input, when the input is this series of impulses, and I've sketched it out here. So it's 4 at 2, 3 at 3, 2 at 4, and 1 at 5. Okay, and it's 0 everywhere else. And just for convenience here, I've resketched the impulse response of the system. So when we see an input of this form, it's sort of an arbitrary input consisting of a series of impulses, and we have the impulse response, one immediate way to solve for the output is to do the convolution, right? So that we know that we can write y2 of n is the convolution of the input with the impulse response of the system. We have both of those things, so it's quite easy to solve for the output using this. And we can write the convolution sum two different ways. We can write it as the sum x2 of k, h of n minus k, and we're summing over all k. Or we can write it as the sum over k of h of k, x2 of n minus k. So what we're basically saying here is we can, convolution, as we know, is we're looking at a flipping and shifting and summing operation, and we know, because of the commutative property of convolution, that we can choose to flip either x2 or h in this problem, and we usually pick the easier one to flip. So if we look at these two signals, the x2 and the h, it's kind of arbitrary deciding which one is easier to flip, but since this one starts at 0 and it's just all ones, it's probably easier to flip that one. So for that reason, I would suggest that what we should do is we should implement this version of the convolution, meaning that we'll flip the h and leave x2 alone. All right, so we're going to need a flipped version of h, so let's just sketch that for ourselves here. If we're going to sketch h of minus k, well, first, technically, we'd have to sketch h of k, but to do that, we could just rewrite and just erase where we saw n and stick k in there. Right? It's just a different summing index, or a different index, but the signal looks exactly the same. We could do the same thing over here so that we would have x2 of k. And so we'll just write that as a function of k. Okay, so h of minus k is just a flipped signal. So we take this and flip it. And we're flipping it, remember, around about the y-axis. So we're going to flip it around here. And if I do that, now the signal at 0 stays at 0, but now that's at minus 1, minus 2, minus 3. We haven't changed the amplitude values at all. And that's a function of k. And then the other thing that we need down here in this equation is we need, whoops, I wanted my pointer back. We need h of n minus k, right? Well, h of n minus k is just a shifted version of this. So let's just get that sketched. H of n minus k. Now we've shifted it, and so now what used to be at 0 is at n. So we've just taken this point and moved it to n. Remember, we're sketching these as a function of k. So this over here is at n minus 3, and that's at n minus 2, that's at n minus 1. Okay, so now I have a sketch of x2 of k, I have a sketch of h of n minus k, where n is a variable, so that moves, right? As I make n very large negative, the signal is shifted over here. As I make it very large positive, it's shifted over there. And so I'm going to successively calculate outputs for each possible n, multiply the two signals and then compute the sum. So let's do this on another slide. Okay, so I've just repeated my sketches of x2 of k and h of n minus k. And so if I look at this, if n is really, really a large negative number, then this signal shifted all the way over here. And when I multiply them together, there's no overlap of these signals. So the zeros in this signal multiply with the non-zeros down here, and the zeros here multiply with the non-zeros up here. So we know that for n less than, let's see, look over here. If n is less than 2, when I multiply those signals together, I get nothing. So for n less than 2, y2 of n is going to be equal to 0. Because again, I'm computing this summation. I multiply the two signals together and then I add up all the values. I can also see that once I've shifted way far over here, and if I shift so far that this point goes beyond 5, then I also am multiplying zeros together, and so I can say for n minus 3 greater than 5, y2 of n also has to be equal to 0. So that's n greater than 8. So the non-zero values of the output are going to lie between 2 and 8, which makes sense because from other work we've done in class, we know that to find the starting point of the output, we add the starting points of x2 and h2. Starting point of x2 is 2, the starting point of h2 is 0. So the starting point should be 2. We add the ending points. The ending point of x2 is 5. The ending point of h2, if we look on the previous slide, is 3, so that's 8. So this all makes sense, hopefully, over here. In the meanwhile, we're going to actually do the point-by-point calculation. And let me get a graph over here I can sketch it for. So for n less than 2, so we have 0, 1, it's equal to 0. And then we have whatever it's going to do at 2. So what will it be equal to at 2? Well, if n is 2, then I'm lined up so that I'm multiplying 1 times 4, and then everything else is multiplying to come out to 0. So at 2, I get 4. Let me sketch this here. So that's 4. And then at 3, I'm going to shift it over one more. So now n is 3, so this point is aligned here. So I'll have 1 times 3 plus 1 times 4. And all the others are going to be 0. So 1 times 3 plus 1 times 4, if I add those together, that's going to be 7. So that's 7. Get it, 5, 6, 7. It looks like I'm going to need a little more room on my graph here. So let me make a longer axis. 8. And then beyond 8, we know it goes to 0. Okay, so I just continue shifting this guy over. So I shift it over when n is equal to 4. I'll have 1 times 2 plus 1 times 3 plus 1 times 4. So that'll be 2 plus 3, which is 5, plus 4 is 9. So that's 9. If we shift it over to 5, now I've got 1 times 1, 1 times 2, 1 times 3, 1 times 4. So it's just the sum of these. 1 plus 2 plus 3, that's 6, plus 4, that's 10. So I'm at 10, at 5. Should be at 5 there. At 6, now I'm going to shift over. Now this is going to be multiplying a 0, but I'll still have 1 times 1 plus 1 times 2 plus 1 times 3. So it'll be 1, 2, 3 added together. So that will be 6. So that's down here. As I move over to 7, now n is equal to 7, so I'm 2 over here. I've only got 2 non-zero point overlaps. It'll be 1 plus 2, which will be 3. So it'll be 3. And then finally, I'm over where n is 8, and so only n minus 3, which is at 5, lines up here. So it's 1 times 1. And I get 1. Okay, so this is a sketch of y2 of n for this case. we've used graphical convolution to solve for the output in this case. Okay, so that was pretty straightforward. We recognized that when we have an input of this type, we should try to solve it using convolution, since we have the input, a good sketch of it, and we have the impulse response. And graphical convolution is useful to have. There have been some other videos posted, many other videos posted on graphical convolution, so you should check those out if you're still having difficulty computing graphical convolutions. But hopefully this has given you a little more practice. Alright, so this video was made for the ECE 201 course at George Mason in the fall 2015 semester. If you want more information about Mason or our Volgino School of Engineering, the ECE department, or the courses I'm teaching, you can check out these websites. Thanks for listening.